Swayam Prabha. Digital India. Educated India.
We're still going to wait a couple more minutes before we dive into this, but it's too quiet in here. So I know some of you are visiting. I am visiting this area. I just thought I'd share a little bit about my weekend. I was so thankful that the rain held off for today. I had a chance to go to a living museum, Dakshin Chitra, on Saturday. I learned a lot about southern India, both historically and current, and food and culture. We saw dancing and music and food. I got mendied. So that was my my excitement for Saturday. And then yesterday I had a more adventurous outing. One of our Clarkson PhD students is from Chennai, and so he's actually home here visiting. So he took me out on his moped on the streets, which was a little scary, but he knows me that I am somewhat adventurous. So he didn't think twice about doing that. And we went to, I know him from Clarkson mostly because he's very active in our garden club. We have a garden on campus and a greenhouse. And so he took me to a nursery. It was sort of on the, well, you weren't there, where we drove on Saturday. We went back down that way again, and just like an acre of plants. And it's good. It was good to see plants that are like house plants in New York State, where I'm from, grow outside here. So we got to see a lot of that, more tropical in nature, so that they don't live outside at home. So that was good. And then we went to the beach and got blown by the wind, hit by sand, and then we went out to a really interesting restaurant. So I was very happy to have some non-rainy day and then outing on a moped. I figured that was about as India as an experience as I can get here. So that was my weekend. Anybody else who is visiting do anything interesting? I already told them about Dakshin Chitra. So my goal this morning is to go the next step in detail about life cycle assessment. We introduced the concept last week about what it is and the general ways of thinking. Today, we're going to start talking about how do you actually do it. And it's really hard, you know, in the scope of what we have here today, it's really hard to do a life cycle assessment. So we're not expecting you to do a life cycle assessment, but we're going to give you an opportunity to do little pieces of it on these case study projects that you are working on. So you will work on that. So I just wanted to start. So this is plastic water bottles, and I'm going to talk about plastic water bottles again this morning. I introduced those last week. What are the life cycle stages that we see? This is just review of nomenclature for you. Life cycle stages. Speak up. Resource acquisition, actually, yeah. And so it's presented here as extraction of raw materials. That's resource acquisition. Okay. Manufacturing. We have production, packaging, distribution. That's manufacturing.
Transportation.
Transportation is not shown on here, but that would be part of this. Yep. Use, yes, use and maintenance. And end of life, which is shown here as disposal, which can include our circular economy of reuse and recycling, or going off for. So those are the life cycle stages. What's not shown on here, but I'm still going to ask, what do you think the environmental impacts are of a water bottle? That's what we're going to talk a lot about this morning. Environmental impacts.
GHG emissions.
Okay. Greenhouse gas emissions. Water use, absolutely. Microplastics, is that an environmental impact? It is a
Microplastic pollution.
microplastic pollution. Okay, so water use and pollution. I guess that's soil. But pollution itself is not really an impact. What is the next step? You have pollution, and then what's the next step of microplastics? Because we have microplastics in the environment, what are the
PM,
say,
particulate matter.
particulate matter is a different one, but what's the impact of particulate health? Okay, so we have human health. So like toxicity. Okay. So we have the causes, right? So, but then we also have the impacts. All right. So I heard some other things here.
Aquatic life.
Aquatic. So what about aquatic life?
Species will take that microplastics and it will affect human life.
Okay. And what's for the aquatic life, that's the exposure route. What's the impact?
Feminization in fishes. Feminization in fishes.
Okay, feminization. So that's one particular feminization of fishes and amphibians also, but maybe we can call that ecotoxicity. Right? These are the impacts. So you're good at the outputs. Okay, so what are the other impacts? Now, and greenhouse gas emissions, that's really global warming, right? Or climate change. Any other environmental impacts?
Effect on resource.
Okay, resource depletion, absolutely. Like, for example, water, right? Anything else?
Change in land use patterns.
Land use. All right. So I just wanted to get you thinking about, we have the outcomes of this plastic, like the microplastics, the greenhouse gas emissions, the water use, but then all of those cause impacts. So it's like that next step. It's like why are we concerned about greenhouse gas emissions and water use? So that is what we're going to talk about a lot today. We'll get there. So we're going to start with some inventory still, and then we're going to get to these impacts. So there's two groups of words there that we need to think about. So hopefully that opened your mind to those different things. All right, so again, this is just review of last week. We have our life cycle stages. You've got all those back. We've got our inputs, which are the raw materials and energy, and then the outputs. And you were good about some of like the outputs, the microplastics, the particulate matter, all of those are outputs. And then the final thing that we have to still do is to think about how do those inputs and outputs affect the environment and society, humans and the environment. And so that's where we're going today, is trying to put all these pieces together. So I shared this with you last week. So this is just sort of a reminder of some of our words, and things like the system boundary is really important to think about, especially when it comes time to, like, you're thinking about your projects. You're going to have somewhat unusual system boundaries just because the amount of time and data that we have to share. You won't be doing full life cycle assessments. So let's just look at an example of paper or plastic bags, something I've been paying attention to here. So we have different types of bags. So paper bag, a paper bag is, this one has 30% recycled fiber. Compostable plastics, usually that's a plastic called PLA or polylactic acid. Is the most common compostable plastic. I'm not sure that it's compostable. They claim it's compostable, and then polyethylene, which is sort of your standard grocery bag. And so in this particular life cycle assessment, which is pretty old, the categories that they looked at were energy, fossil fuel use, municipal solid waste generated, greenhouse gas emissions, and fresh water. So are those impact categories? Are those impacts? Some are inputs, some are outputs. That's okay. Are they really the consequences of the different bag use? So I would put these, we're going to call these are more life cycle inventory. Outputs or results. It's how much of stuff. How much of the stuff goes in and comes out. So it does have the inputs and the outputs, but it's really not human toxicity, right? It's not global warming. So I guess it does have greenhouse gas emissions. So that one is sort of the exception. But we can still do interpretation. So that's a really, really important step with any life cycle assessment. And you can do interpretation after a life cycle inventory or after a life cycle impact assessment. And we're going to talk about both. So if we look at these, so you can probably imagine the red are the worst and the green are the best. So what looks like the best bag? And the functional unit here let's look at that for a second before I move forward. Is the carrying capacity equivalent of 1,000 paper bags? Why do you think we're not just comparing one compostable to one paper to one polyethylene bag?
They have different strength.
Different what?
Different strength.
Different strengths, right? So can you put as much into a plastic bag as you can a paper bag? No, both volume and strength. So sometimes they get double bagged, right? So you put two bags together in order to like if you're carrying a gallon of milk or cans of something, that is that's much it's much harder to carry the same weight in a plastic bag. So the functional, right? So this is good. They came up with a function that was equal across, not one to one to one, but an equivalent function. But still, even with that, what came out best? You should all know this from what's on the screen. Polyethylene, is that a surprise? Maybe, right? So what's going on in India right now with plastic bags?
On paper, it is banned, but still they continue to use.
Okay. And I'm going to talk about that some, I think, Wednesday or Thursday. I'll talk more about some of the politics associated with some of these. But this shows us that the polyethylene is best. But it's the best for these 5 inventory categories. What's missing, do you think, that maybe a polyethylene bag might be worse than a paper bag? Anything?
Just cradle to gate? Is this only cradle to
This is, no, this is all the way through, because municipal solid waste is there.
It's not compostable at the end. One bag.
Well, okay, so it's just saying how much municipal solid waste is generated. It's not saying what's happening to it. All right, so does not include. Right, so it does not include the ultimate fate. Okay, anything else that you might think that plastic, what were we just talking about on the previous slide? What might be different between, or something we were talking about with the environmental impacts of a plastic life cycle? Toxicity, there's no toxicity. No consideration of microplastics or even making plastics. There's lots of organic, volatile organic and toxic materials released during the refining process and the fossil fuel development process. So there's a lot of stuff that's not included in this. So, and of course, this was done by the plastic bag industry. And so they picked impact, or not impact categories, but these are truly just inventory results that they liked. And the polypropylene looks the best. But in reality, paper is not great either. It uses a huge amount of water. There's a lot of chemicals to break down the lignins from the tree or bamboo or whatever you're using into pulp. It takes a lot of energy. So it's not great. Paper bags aren't great either. And so that's why we've changed again. So our circular economy solution is cloth bags, absolutely. Right. So reusable, right? Anytime we put that reuse word in there, we know that we're doing better. And that wasn't even included here. And some people say that that is bad because you use a lot of use if you wash it. But how many people wash their cloth bags every time they go shopping? Any of you? We don't buy, if you buy meat, it's one thing because the packages might, right? But if you don't buy meat, is really, they don't get that dirty. Maybe milk but anyhow, we don't wash our canvas bags that often. But the ones that make cloth bags look bad generally make unreasonable assumptions about how many times they get washed. And then washed in hot water. And then between the energy and water used in the washing, so in the use phase, it looks really bad. So you can skew these. All right. So these are good eco indicators, but they're not typical impact categories. So let's get back to the steps. So we just did interpretation though, right? We were able to do interpretation even with the inventory analysis. We talked about the scoping. That's where you set your system boundaries, set your functional unit. The inventory is when you think about all the inputs, mass and energy amounts, and all the outputs, but you don't connect those then to the impact. And so today we're going to talk a little bit about inventory and then connect those to, well, how do you go from this number to a toxicity? We will do that today. And then the improvement or interpretation is how do you interpret those to figure out how to do better? So we are going to go through some of these steps today. All right, so the inventory. So we started this last week. First step is that schematic diagram where you identify all the flows, and the goal is to put numbers on those. And that's what we're going to start to do. If Bindu can get here with your paper without ruining them in the rain, we will start to look at that, trying to quantify. So you'll get more numbers for your project today. It's all the energy and raw materials used and all the emissions to the air, water, soil, solid waste, all of that together. Then the inventory, got lots of processes, lots of numbers. When you put all that together and you figure, what's the total energy used? What's the total energy used in manufacturing? That is sort of the end of an inventory. So it tells us, for the whole system or broken down by stages, what all those resources used and emissions are. So that's the overall step in a life cycle assessment. And we went through this slide the other day, the types of information that you need to really do this. It's a lot of work. Like this is generally like a master's thesis sort of. If you don't have a lot of information, you're not using somebody else's life cycle assessment. This is a lot of work to try to come up with all of that. So we're going to look again at this water bottle life cycle, and I've got two studies that I'm going to share with you. One that is more basic. So this came from the National Institutes of Health at the United States. So this was the starting. And so last week you thought about the whole life cycle, right? And we're not going to have time to go back to those schematic diagrams, but that's all right. You thought through all the pieces and parts that it took to make a PET water bottle. So let's see what the NIH did. So summary results. This is really life cycle inventory again. So looking at energy consumption. So this is a 500 milliliter PET bottle. And so this is energy consumption. And it does not include the, I will show you in a minute the disposal. So this is material production is the biggest, right? Making that PET resin, and then the bottle fabrication, smaller. The water part is minimal, right? The water that, right? I made you all think about that, but that really ends up being minimal, at least in terms of energy and consumer use. That's mostly refrigeration. So the total is 2.27 megajoules. I think this is, yeah, megajoules per bottle. If we also look at now, this is the disposal, it's still megajoules energy, but it's they're negative for incineration and recycling. It's negative for incineration because energy can be recovered, absolutely. And it's a bigger negative number for recycling because
like the raw materials will again go into that.
right, you can skip a lot of this material production. So that embodied energy that's part of the plastic water bottle, you can't skip it all because you still have to put some amount of energy into recycling, but you don't need to use as much energy as the raw material. So it's less than half. It's about a third, right? So you're doing much, much better. But look at the total numbers. Recycling compared to 2.27. So even the best end-of-life treatment disposal option still is pretty small. Right? Even if we do the best we can, it still doesn't really overcome the rest of the life cycle. So this is something, an interpretation that is important with water bottles. What can you do that's better than recycling? Reuse or repurpose, or we still got to get smaller circle on that big diagram.
Refurbish.
What?
Refurbish.
Refurbish. You still do better. Redesign maybe, but you still have a plastic water bottle. What can you as a consumer do? I see it all over this room. Refuse, right? The first R is refuse. So if you don't take a plastic water bottle, you don't have to worry about any of this. You still might need, thank you, yes, your water bottle. You still need to treat the water, right? That's pretty small. And you need to make stainless steel water bottle, which is not inconsequential. So just make sure you use them a lot of times. All right, so yes, refuse, the first R. All right, now here are the greenhouse gas emissions. And this is just, again, the material production is the biggest number, but bottle fabrication is pretty big, as is consumer use. That's from refrigeration. So the total is 0.12 kilograms of carbon dioxide equivalents per bottle. And again, disposal, the best we can do is recycling. But again, this is an order of magnitude smaller number. So it's not very negative compared to everything else. So even if we do better, right? People say, oh, you got to do better recycling. It's not going to help that much. Better than not recycling. And of course, incineration is plus because you're taking the carbon molecules in that water bottle and putting them back into the atmosphere. And landfilling is pretty neutral, right? We saw that. It goes into landfill and it sits there forever and ever until somebody digs it out and sends it to a RFD, refuse-derived fuel. And then basically it's like incineration after it's been stored in a landfill or a dump for a lot of years. So what are the interpretations? Interpretations from this life cycle assessment where we had two inventory results, greenhouse gas emissions and energy use. Material production contributes the highest. Absolutely. And those are exactly the kinds of interpretations that we're trying to figure out. So if we want to do better, we could fix the material. Any ideas for how, if we still have a water bottle, how we might cut the material production?
Distillery has reduced the amount of plastic they are using in bottle cap.
Okay, reduce the amount of plastic they're using in the bottle cap. They've also greatly reduced the amount of plastic. They like cutting this number in half if they're just using 2/3 or half of the material. Some water bottles are so squishy, I can't open them, right? They just like you try to hold it and it just like, right? But it's cutting these numbers. So yeah, so we can tweak the system. We can redesign, re-engineer the system to have less material, and therefore we cut at least that material production. Okay, any other interpretations?
Better machine efficiency, production machine.
So maybe you can improve the efficiency of the machines, right? Maybe you can, we don't know what the efficiency of the material use or heat loss, maybe they can recover heat. There's all sorts of ways maybe to improve the manufacturing process, but we know where to look, right? We know it's that material. It doesn't really make a huge amount of sense to put all our efforts in improving recycling, right? Improving recycling helps, but it doesn't help everything. So it gives us some perspective on where to look to make the biggest, the best impact. And with water bottles, we always immediately go just to improving recycling, right? That's the primary improvement. So we have a guest today. Welcome. All right, but again, we've got good eco indicators, but they're not necessarily impact categories. But we still could interpret a lot, right? But we didn't look at toxicity, right? We didn't look at water use. So there's a lot of things. So yes, for these two impact categories, we know what to do, but it still is a pretty narrow view, right? And one of the things we're trying to do with the life cycle assessment is to get a broad systems perspective, both the whole life cycle, but also a lot more impact categories if it's possible. And so we're going to look at another water bottle. And so this one compared 4 different water bottle types, and they were trying to look at if you don't use petroleum plastic, if you look instead at recycled, or PLA is polylactic acid, a corn-based bioplastic, and ENSO, I do not know what that is, but it's an additive that makes it more biodegradable than PLA. And so again, the idea is to help the consumer, in this case, understand the impacts and maybe help them think about their choice of just single-use water bottles, right? So it's not helping them choose a reusable water bottle. It's just helping them choose maybe what water bottle, if you do have a single-use water bottle, how to do that better. All right, now this is where I've said you might want to move forward because it's going to be hard to see. All right, so I'm just feeding you. This is the regular PET, and they did this whole schematic diagram. So this little square is the PET, and this is basically the parts that you would have looked at last week in your. So you got to make the resin, blow molding, transportation, and then it goes to this bottle water production and reuse. You have other inputs. You've got a label and a cap. So you're going to make, in this case, polypropylene. The label is low density polyethylene. Then you distribute it to the market. You use it. There's packaging material in there too. And then finally, we have the bottle disposal, and there's some hauling, and in this case, landfilling. They did not look at recycling. So that schematic, even though you might not be able to see this really easily, it's what you thought through last week, right? So this should not be. And over on the right, this is when they were starting their life cycle assessment, these were the numbers that they figured out as input to a life cycle assessment software. So these are sorts of things that you're going to be thinking about right now for your projects. So the direct input, how much kilograms, PET, plastic film, PLA, all the different materials, cardboard for packaging, water, transportation in terms of kilometers, and some of the direct emissions. And for the PET, it's just a waste stream in terms of kilograms. This is what the life cycle practitioner needs to figure out. So the data that we give you today for your projects will help you have some of these numbers. So that's a start. How much about this whole process can you figure out? And then this is just the same thing. They looked at all the different ENSO bottle, PLA bottle, and recycled PET. The rest of it they assumed was the same cap, the same label, the same amount of water treatment, everything else was the same. And so now you've got 4 times as much information that you had to figure out, because now you've got 4 different types of water bottles and you have to figure them all out. So this is the input to a life cycle assessment software. This is what you as the engineer or the life cycle assessment practitioner would have to figure out, this sort of information. And you have to figure out, why just this? Why not more? This is nothing about fossil fuels to make PET, right? So some of the information that you need, you can get from other resources. So this, let me go back. So this little, I'm going to blow up that square right there, the PET and bottle production and transportation. So that was the same bottle as here. So we know from what we looked at last week that we need to use natural gas and oil. So all sorts of refining steps. There's transportation. We make those nurdles, the little tiny plastic beads, white beads. That's really polyethylene terephthalate, or PET. And that's what goes into the resin production. There's a huge amount of refining processes. My undergraduate degree was chemical engineering, but I'll tell you, doing life cycle assessment, I do not have the capacity nor the time to model that huge refining process, right? It's just a huge amount of work to do that. And so the LCA practitioner comes up with ways that they don't have to do that. They use somebody else's work. And that's this software that we use. And Arun's going to show us this afternoon that we don't have to do all of that upstream, what we call the upstream. The PET resin is our starting point for making plastic water bottles. We're going to use somebody else's work to do all the other upstream, all the electricity, all the fossil fuel extraction. Other people have already done that. There's some complications with that, but that's where the software comes in. So we still need to know these numbers, right? You couldn't see those on the other page. And we had the transportation total, how much electricity it takes for the blow molding, and how much resin goes into a water bottle. So we still need to know some things about our particular part, the key to what we're doing as an LCA practitioner, but not all the upstream. So is there our overall approach? You've got your scoping, that was the system boundaries and the functional unit. We had our schematic, quantifying the key inventory input for your critical part of the system. And then we want to go find relevant databases where other people have already done that. And so all of this stuff, we're going to search for life cycle inventories that have already been published. And so there's a source. I'll show you all the different tools later. So this came from Gabi, which is now called Sphera. This is what we use, my students use. Database. So it's polyethylene terephthalate, granulate, bottle grade at the plant. They're already making all that resin. You still have to transport it. You still have to do this from wherever the plant is, but you don't have to figure it all out. It's just really important to make sure that it's relevant and it's a reasonable inventory to use. But yeah, so we can go find that. We do not have to model it ourselves. There are better and worse inventories, but that is, this one is a pretty good relevant inventory. All right, so that helps us with the input, right? We got to put in our inventory that we calculated. We have to find all these other upstream inventories. And then the life cycle assessment software is going to put all that together. It's just basic math. It's just math. It's summing up across life cycle stages, everything that was in the output of those inventories, it's going to amass. And so here's just an example. And this is a tiny, tiny bit of an example just for the atmospheric production of PET resin. So just from that inventory I just showed you, a tiny, tiny fraction of it. So does this make a lot of sense if we're looking for environmental impacts? What environmental impacts do we get out of this? So we know that some of these are toxic, right? We know that some are global warming, right? Does this tell us the toxicity? No, right? It's like I see VOCs unspecified, volatile organic compounds, or hydrocarbons unspecified. Probably some of those are toxic, but I don't know how toxic. Particulate matter, I know that has human health impacts, but I can't tell that from the emissions, from the mass of particulate matter released. I can't convert that in my head to a health impact. So this is why the inventory results are not in this form, for at least for the atmospheric emissions, don't give us the whole story. And so we can't interpret all of that. So for example, we know those top 4 contribute to global warming, but we know that they don't contribute equally. And so this is why we need this life cycle impact assessment to put things, right, this list of 100 into a list of 10 or 12 or 8. That's what the life cycle impact assessment is all about, is grouping things that have the same impact so that we have now 8 or 10 or 12 impact categories to interpret rather than 200 different air emissions. And then there's a separate list for water emissions and solid waste. And so there's all sorts of very long results for the life cycle inventory results. So that brings us to our impact assessment, what we're going to do next. So it's how to transform that inventory into impact. So it's a transform. So all the different resources used, water used, energy used, greenhouse gas emissions, toxic emissions, whether emissions to water, we're going to lump those all in together as potentials to do damage. So for example, you probably have all seen carbon dioxide equivalents before, right? You know the concept of carbon dioxide equivalents? We're going to do the same thing. We're going to have human health equivalents. We're going to have acidification potential in terms of equivalents. So the same thing that you might have already done with global warming, carbon dioxide equivalents, we're going to do with the other impact categories as well. So a lot of science behind this. And sometimes we weight these for importance, but not. So this is what the impact assessment is all about, is to get it into these categories that we can come up with equivalent impacts. So there's different steps. So first you have to figure out which impact categories you're looking for. That's something you might decide at the beginning, depending upon the objectives of your work. And then you have to figure out which LCI results, we call these the stressors or the the inventory results. Which, like NOx has all sorts of different impacts. So we need to know how to match those. And then the characterization is like, how do we come up with the equivalents? Does anyone know the global warming equivalent for methane for global warming? 28, yes, that's the one that's currently used, 28. So on a mass basis, if you have 1 kilogram of methane that has the same global warming impacts as 28 kilograms of carbon dioxide. So that's its equivalence. That's a characterization factor. 28 is a characterization factor that you might be familiar. There's a lot of modeling that went into figuring out that 28, and it's changed with time. 15 years ago, it was 21, then it went up to 25, and now it's 28. Now there's differences, all sorts of other complexities, right? But it's because we understand climate science better. So as we get better at being environmental scientists, we can figure out how to come up with better characterization factors. And then we're not really going to talk about normalization, where you try to get it into one impact number, although we'll look at some results. All right, so let's see, how do we do this impact assessment? So you've already looked at, you've got this big schematic, you've got lots of processes, you've got transportation, manufacturing, extraction, the whole life cycle. So that was your inventory. And then that output, you get all sorts of different emissions, right? So I just have a bunch of air emissions right here and fossil fuel use. Some of the processes, these might contribute to different categories. So if we look at SOx, process 1, 2, and 3 all generate SOx. So we're going to add those all together. We might look at it by process later, but we know that we've got SOx, ammonia, methane, fossil fuel use. This is just made up. So that's our inventory output. So the classification and characterization, the classification is just matching, right? So NOx, SOx, and ammonia all contribute to acidification. They go in the atmosphere, we get sulfur dioxide and nitric acid, not sulfur dioxide. We get sulfuric acid and nitric acid in the atmosphere. It rains down, we get acidification. Methane and carbon dioxide both contribute to global warming. NOx and methane contribute to photochemical smog, and fossil fuel use contributes to natural resource depletion. In reality, we'd have a lot more of these, right? A lot more of these inventory output. But the classification is the matching, and then the characterization is using the characterization factors to multiply out to come up with a number. I'll show you an example. And in some cases, there's ways to add those together into a unique factor. And I'll show you some results, but we don't have time to get into that. So that's the basic idea, right? So we've gone from maybe 200 inventory output to, in this case, 4 impact categories. And they're the impacts, they're not the emissions. The emissions are the inventory output. All right, so I use one tool. This is the US EPA, and it's written for the US, but I really like this diagram that sort of shows that whole thing. So we have our inventory of stressors, right? All those chemical emissions and use. We have the impact categories, right? So we've got the matching here. And then what we don't have to do, because the science has been done, there's been a lot of environmental science and exposure assessment and risk analysis that goes into coming up with these characterization factors. Like the 28 for methane, right? That's a lot of climate science went into that. If it's toxicity, you've got to have a lot of exposure assessment and toxicology. Scientists have done that. And so the LCIA, life cycle impact assessment methods agglomerated all of that information and data to come up with these characterization factors. They are not perfect, but they help us do the work. So that's work we don't have to do as life cycle practitioners because it's been done for us by these life cycle assessment methods. And then we get graphs of all our different impacts, human health, non-cancer, for example, or ozone depletion. And so that diagram sort of puts it all together. So your job is the inventory of stressors, matching it to the impact categories. Then software, we're going to play around with doing a little bit of calculations, hopefully here. Software does multiplies it by the characterization factors and comes up with the results. There are different life cycle impact methods. I use something I use Tracy for the work that we do that's US specific. We also use something called Recipe. It's an acronym that I can't ever remember what it's. There's CML, there's Impact 2002, I think the number is. There's all sorts of different methods. And they have different characterization factors and they might have different impact categories. And it's okay to use any of those. Sometimes it's good to use a couple of them just to see if your interpretation can change, but there's lots available. All right, so how do we do this? So we know, so this is this modeling of a particular category for the impact data. The only thing that we have to do is this equation. So we have our characterization factors times our inventory data, which is often mass, right? So you might have a characterization factor, that would be 28 for methane, times the mass of methane. Then we can add carbon dioxide and methane together. Otherwise, you cannot just add mass of carbon dioxide plus mass of methane. You can add them together, the summation, if we've converted them to carbon dioxide equivalents, right? They have to have the same units to add them together. So this is really just about getting everything in the same units so they're comparable, so we can add them together. This is our key equation. The overall impact is the sum of, for each stressor, each inventory output result that you have times its characterization factor that contribute to that emission. All right. So does that make sense? It's just simple, very simple math. The math in all of this is very simple. It's just finding all the right numbers that is more complicated. And you have it's the accounting. Life cycle assessment is really about accounting and keeping all these numbers straight. And that's where the software can really help. I use Excel a lot too, and you can do an awful lot in Excel or some other spreadsheet, but it's hard. All right, so let's look at an example. So we already know this is the same table I showed you earlier, that we have several of these. Right, so this would be the classification. Is identifying those emissions that contribute to a particular impact category, in this case, global warming. And then we can go and we can look for what are called the global warming potentials. So this came from the IPCC, the International something of climate change panel, thank you. I can't think of acronyms on the spot sometimes. You get so used to just the acronym. So here it is. So this one, methane fossil has almost 30 is the latest number for fossil methane. So it's a little bit higher than, but it has changed over the years. So this is the latest that I could find. So I just looked for this. And so this was from August 2024. So it was fairly recent. All right, so now we have to do that equation, right? Impact equals the sum of the mass. So we've got our mass, right? Here's our mass, and here are our characterization factors. So the global warming potential. So we've got, this is the mass of carbon dioxide times the characterization factor for carbon dioxide, and it's going to our kilograms of carbon dioxide cancel out, and I end up with kilograms of carbon dioxide equivalent. It's really easy for carbon dioxide because it's 1, right? If we go to methane, so our mass of methane, 13.1 times the characterization factor for methane. And the characterization factors do have units. I am always harp on my students about paying attention to units. It does have units, and the kilograms of methane cancel out, and we end up with kilograms of carbon dioxide. We also do that with nitrous oxide, and we end up with 2,795 kilograms of carbon dioxide equivalents, 86% of which was from the carbon dioxide. So most of it was from the carbon dioxide. The nitrous oxide is minimal, but methane is important, right? Making PET, methane, and oil were starting ingredients. So you would expect that there would be fugitive emissions of methane along the life cycle. So that's simple. That is all we have to do for characterization. So it was that equation, the sum of the characterization factors that you have to look up. And it's easier to find them for global warming than others times the mass. So that was an example. So one of the reasons why I like Tracy, even though it's US, they're Excel spreadsheets of tables. And so here's a little piece of an Excel spreadsheet that sort of matches fossil fuel emissions. So we have these are our impact categories. And all these numbers are those characterization factors. And so for global warming, and it's already classified for you, right? So you can see which emission has which impact. So if we look at NOx, what does NOx do to the environment? Environmental impacts. Photochemical smog, yeah. Eutrophication, acidification, and human health from particulate matter. So when you emit NOx, you have to account for it in this case, there might be more, but in this little case, you have to account for it in 4 different categories. So there's a lot there. So it's already classified. And particulate matter, it's not just the PM that's released that causes particulate matter. We also had NOx and carbon monoxide because they react together. Same thing with photochemical smog. They both contribute to photochemical smog, as do some others. So you can get a whole big table of this. So our characterization factors. All right, so I just want to do a practice problem, but I think I'm just, given the time, we started 15 minutes late, I'm going to not do the practice problem. I'm not going to ask you to do the practice problem, but I'm going to show you my spreadsheet with the results. Is that okay? And most of you don't have computers out anyhow, so by the time we get computers out, it'll take too long. All right, so we have our Tracy. So this is the exact table I just showed. So we have our characterization factors, and then we have our life cycle. So this is what was, so here are the emissions, the air emissions, and this is just from the PET resin generation. So you'd have the same result for other life cycle stages as well. So what do I have to do? I have characterization factors and masses. What do I have to do with these? Multiply, yes, mass times its appropriate characterization factors, and then sum, right? So are you all, I assume, spreadsheet literate, good at spreadsheets? Yes, hopefully. My students, I have to teach them. All right, so here I have characterization mass, and so I just have the equation. I don't know if he says this, it's I had them all aligned, so they're in the same row. So and I can copy over. So I've got Tracy, B5 is the characterization factor for fossil fuel depletion for coal, times So I've got B5 times B5. So let's just go look. So I had B5. So the characterization factor for fossil fuel depletion times B5, the energy used per kilogram of PET resin. And then I get the multiplication. And I do that for all of them. And this was like a 5-minute spreadsheet. And then I do my sum. So now I have a total. So I have my impact categories. You still might say, well, how do I interpret these? One of the things that I like to do is to figure out, well, what caused the high scores? So for fossil fuel depletion, 50% of it was because of petroleum. For the global warming, 85% was from carbon dioxide, not from methane. SOx, so you can see that NOx is the predominant contributor for both eutrophication and smog, and PM 2.5 causes the biggest health impacts, and SOx is the biggest contributor for the acidification. And this is just for the PET resin production, right? You do the same thing for the bottle manufacturing, the use, the refrigerator use, the transportation. You would then have different LCI results for each of those different life cycle stages. And then you could also add across life cycle stages. This is just for one stage. Right? But the math is easy. It's the accounting and, keeping your spreadsheets organized and efficient. You can, teaching students how to do efficient spreadsheets is the hardest thing. A lot of my students can use spreadsheets, but they make each equation individually rather than drag and you're all done. So anyhow, you got to set it up well. But this is what the software would do. Like what Arun is going to show you this afternoon, it would do all of this calculation. It would find those characterization factors. I'm sure he's using a different method. What do you use, Arun, for your impact assessment method? What do you use for your impact assessment? Say? Recipe. Okay, which I said is pretty typical. So not Tracy. So he'd have different characterization factors, but the software is doing it for him. So this is just, you can do it this way, but when you have hundreds, this gets really hard. All right, I just wanted to show you the math behind it. That's right. So that's what, there are biases. Yeah. So I'd say right now, recipe is probably used most frequently, at least in the research, academia. Recipe is pretty standardly used. We just did one and we compared trace for electricity in the Northeast United States, and we compared Tracy and recipe, and we also compared databases, which I'll show you. Like, where do you get all that upstream data? Huge differences, but it was more from the databases. So you've got to be careful about the databases, which are they relevant? But the best thing I think to do whenever you do a life cycle assessment at all stages is to do what we call a sensitivity analysis and to try different things and see if there are impacts, because there are uncertainties in every step, right? All those numbers for your life cycle inventory input that you figure out, you don't know those numbers precisely, right? They're guesses. Better if you had some distribution of values or a range, because you're not sure about so there's uncertainty, therefore you do sensitivity analysis and you figure out what's most important. We don't have time to go into that this week, but there are definite best practices to think about that uncertainty and the differences. So best to find, and in most, and even life cycle assessments in the peer-reviewed literature are often, if I was a reviewer of those papers, I would not. So there's one that actually I found for, I don't remember which one, data for one of your projects. I found data, but it was not a great life cycle assessment. But anyhow, it was what I could find for you. I did the work to try to pull some numbers together. Bindu helped and some, but there's a lot there. Okay, so I just want to look at, remember that more detailed life cycle assessment. And again, this is, I can read it up there, so maybe you can read it down here. So they used a different, so this was from 2018, I think, Impact 2020. And they used software, SEMA Pro. So they have lots of different impact categories now across their the 4 different water bottles that they looked at. And now I forget that they color coded these. So the darker green are the highest scores, and the lighter green are the second highest scores. So I just forgot. So if we look at this, right, regular PET, that's our standard water bottle. And one of the questions here was, should we change it to something either recycled or something that has more plant-based starting materials in order to reduce the environmental impact? What do you think, looking at this, in terms of the best approach? Can we do better than regular PET? But they all have some worst case things, right? But if you look at like aquatic eutrophication, all the numbers are the same order of magnitude. They're not that different. Some of these, if you look at carcinogens, the regular PET is like an order of magnitude higher than the recycled PET. That's a big difference, right? So you got to think about the relative numbers too, not just this. The color coding was in the paper. So let's see what else is big numbers. The aquatic ecotoxicity, they're all about the same number, right? They're not that much different. So you can do some more math and, you know, look at the relative value of these. And that's often how these are presented, relative to each other, how good or bad they are. But nothing stands out like it's just the best everywhere. Right? But recycled PET, the highest is aquatic eutrophication, but it's not that much higher than the others. Non-carcinogens, you know, those numbers are about all the same. So it really, I would say the recycled one looks the best. The ENSO, the global warming is about twice the others, right? Maybe that's important to us. We don't want something that's twice as high. So it takes a while to look at these numbers and figure things out. So the PLA has the most number of highest impact, although some are like, they're the highest, but not too much higher. So I would have not colored them all. Regular PET has the second number of highest values, and ENSO by far has the highest global warming, right? So this is where trade-off time, but you have some numbers to think about, right? You can actually compare these with some reasonable implications. So that's one way to think about life cycle assessment is, and these are the totals, but it doesn't tell us how to improve any of these, right? It just tells us the difference between these products. If we look at this way of, I can't move that. So this is just for the regular PET water bottle. So you would have a graph like this for each of the 4, but it breaks down by life cycle stages. Those are the colors and impact categories. So the dark blue is the bottle manufacturing. And you can see a lot of dark blue, right? So just visually by color, if you're colorblind, but visually by color, you can say, well, that bottle manufacturing is really a big part of that. And this includes the making the PET itself, the raw material. So this is the bottle manufacturer, and everything upstream is the biggest category. The distribution centers, they're pretty big too, the orange on several things. And I think that's probably from refrigeration. They're the sorts of things that look like they are associated with electricity. So you get now some sense of where the problems are. And so now you can start the improvement analysis, tackling which life cycle stage you want to try to improve. So this really helps the improvement analysis, right? So the comparing the bottles, like they all have problems. Everything that we use has environmental impacts, right? There's no win-win for environmental impacts, just other than refuse. So our interpretation from this, so PET and bottle manufacture is the greatest overall, right? Distribution center is significant in many categories. But if you look at the end of life contributions, it's the end of life. I figured it out this morning. Disposal. That's the light blue way down at the bottom. I don't know if this will work. This is disposal. And that assumed landfill. Pretty minimal, right? So again, just like that simple life cycle assessment that we started with, I've shown you 2 life cycle assessments for water bottles. Both have shown that the disposal phase is minimal. Now this one has lots of categories, right? The other one just had energy use and greenhouse gases, and we concluded that the disposal life cycle stage is minimal. This one comes up with the same answer across many, many impact categories. But that's where usually when we think about policies and people's mind, they see end of life. That's what we see as everyday consumers. It's what we're concerned with. And this does not cover litter, right? You got to write that this does not cover litter. When it says disposal, it is looking at proper landfill disposal. There is no littering in life cycle assessment. So we've got to remember that there are limitations in what we do here. So it's not there. All right, so I just wanted to share those kinds of results and what you can do with the results. The interpretation is why and improvement is why we do life cycle assessment. It's not just to come up with the numbers. It's like, how can we compare? How can we do better? And with these results, we can really do that. I just wanted to share with you some life cycle impact assessment methods end up with a single score. And so here's just 4 large categories of materials. And some of you, these, I don't know if anyone, but it helps you understand where you might want to improve. So like large electrical, like a refrigerator, a washing machine, a dryer, clothes dryer. The biggest impact is during the energy use. It doesn't tell you what the impacts are, but the biggest impact by putting all these results together. So if you want to improve, you look at this graph and you say, I need to work on making it more energy efficient, or I need to find a different energy source, right, to put into it. But the typical energy sources, but if you look at electronics, where's the biggest materials and manufacturing. You don't worry as much about how much electricity goes in, about all those different rare earths, your laptop, the manufacture of all the semiconductor industry, all of that there. So if you want to fix your laptop, make it less impactful, you manufacturing. That's why these. And then if it's often washed apparel, right? So lots, right? Well, so we've got one group here looking at a cotton. If you just look at this and say, well, here's the results might look like, broad organic, but what do you fix?
Embodied is already
Which?
embodied energy is already high in terms of transport.
Yeah, right. So half of it. Yeah. Wash less frequently. I learned that during COVID. my clothes after every single day, right? And things. I was home. I didn't have to go to work. Not wash. So you could wash less. If you washed it half, as yellow bar gets half. Okay. And the embodied energy is half of this, right? Prevent. How do you improve to make sure your personal overall impact? Any ideas? Even do better than that. So that's one. A textile, maybe they're better in India. You do more textile work. Very bad textile recycling. It's down. What else do you do with your clothes to that embodied energy? Reuse. Wear, right? No fast fashions. The biggest, you know that term? Yeah. It is half is the embodied energy. You don't want to know how old this dress is. You know, every year you want the latest fashion. You're throwing away that embodied energy. So wear over and over and don't wash it as much. These very simple diagrams, you can still come up with analysis and think about the life cycle thinking. Let's see. So far. This is what we talked about. Present two things. We do access to a couple of spreadsheets. Bindu provided that has energy and for a lot of different materials. Access to the you have to pay for that. There's a lot of these you have to pay for. And so this afternoon, we're going to start in our schematics and looking for in some of the resources that we. So there's a lot of software out there. You still have to understand your system. You still have your schematic. You still have to figure out what a function makes sense for your objectives. You still have the system boundaries, cradle to gate, cradle. It's your LCA expert. If you have money, you can buy software. Otherwise, you can use a lot of the tools we've been looking at this past week. Water, you can use those. It's just a bunch of math and accounting. That multiplication and adding, that's here. It's keeping track of all of it is what spreadsheet for a simple problem, or the soft spreadsheet to organize your simple problems, or software to do your other. You have to figure out how to best present your results by cycle stage. Just I showed you two different ways. Also, what I call these LCA light, sort of like calculators. Somebody did a life cycle assessment. They put them in the footprint calculator. It's now just them, right? It's not doing did the whole LCA, but right, there are results from an LCA that go into gas footprint calculators, right? And they become for you, but they're still easy and quick point to figure out or activities. Well, there is an ISO. That's sort of the recognized approach to. On the left are all the software. Open LCA is free, and the math. Pro, I think we're going to see SEMA Pro and Open LCA. Just SEMA Pro. So interested in that. My students use, which is the same thing. It seemed like it gave us better databases. With a lot of those is you still need these LCA databases. Remember that whole making the polynomials, all that upstream stuff, you will have access to the databases. And so use OpenLCA, which is free, you still might have to pay for it. So it's still not free. And the global access just helps you to find what has a database that you're looking for. So all of this is really beyond what we're going to do in this class. We don't have time to do this, but there are a lot of tools out there, and I've given you lots of links there to do that. So to summarize, the life cycle impact assessment translates all those massive emissions and massive resources used into a reasonable number of impact categories that we can manage and look at. But even that water bottle example, there might have been, I don't know, 15 there, right? That was a lot. We didn't look at every single one, and I don't really care about every single one, but it's fewer than the inventory output, inventory results, many, many, many emissions. So somebody had to understand environmental science and human exposure assessment toxicity to make those characterization factors. It's important for you as an LCA practitioner to also understand, why does NOx contribute to acidification and smog and eutrophication and particulate matter? It's important for you to also understand some of that, because you need to make sense of it, right? Otherwise, it's just like using AI and not reading and understanding, right? You need to be smart about what you're looking at. And then the steps, you just have to think about what impact categories, what method you're going to use. The math is simple, but it might be big data math. And so simple projects you might be able to do on a spreadsheet, like the example I showed. But when they get big, then using the software is very useful. But it's just a tool to help you do the accounting and to have access to things like recipe versus CML, right? You can do that just at a click of a button, and you can compare the two. You don't have to go find all those characterization factors, they're built in. And that's where these LCA databases, that's what's key to helping make sure that we don't have to do all the chemical engineering refinery modeling. It's already there, but you have to make sure you're using relevant and good databases.